Good afternoon, everyone. This is building data-driven, high-performance internet-scale application with AWS databases. We'll go through reference architectures and giving you the best practices, the right tool to build your internet-scale applications. Internet apps, but with a data focus, so that's why there's this AWS database in the title, and achieving high performance and real time. Very important for internet application. My name is Bastien Leblanc. I'm a solution architect based out of the London office. And I'm very pleased to be joined by Phil McMahon from The Guardian that will talk about his story around migrating from MongoDB to RDF Postgres and the why and the how they did it. So we'll start with explaining what we think of modern internet app at scale and dig into specifically databases. Then Phil will go through the why and how they moved to RDF Postgres. And I'll wrap up with talking about real-time applications and how does it mean and how to implement things like Elasticache or DynamoDB accelerator. So what are internet scale apps? So when developing new apps for the cloud, you have to remember that these three apps are very different characteristics. From the user point of view, they can go from 0 to millions users very quickly. From the user point of view, also, it's global by nature. When you deploy a new app, you don't really expect or know when and how and where it will be deployed, so it needs to be globally available. And the customer expect, and the application expect, a read and write to the database at very high rates, millions of requests, as we'll see with a few customer examples and the Guardian too. And it can be only one or two of these characteristics, global, just high rate or massive user scale. And all these characteristics need to have a proper and good designed applications architecture. So these apps powers the world's largest providers in the world, such as Samsung, Snapchat, or Amazon.com. And for example, for Amazon, we peak at 20 million requests per second during large events like the Black Friday. And if you think about it, 20 million requests per second, it's really large. And if you had tried to do this with a SQL database, even with Aurora, you could only achieve about 500K per second on one node. And so even with the 15 read replicas, you can't even reach these 20 million requests per second. And that's where DynamoDB has been used massively on the Amazon retail website. And also, I was mentioning Snapchat using DynamoDB to reach until 150 million active users at peak time, Christmas, New Year's, things like this, and Samsung on the update of users. So how does it look like from an architecture principle? So to achieve the right scale, you have to design your architecture properly. That's one internet scale reference architecture built on AWS. So if you start from the customer point of view, which is how you should design your application, is look at how the latency from the user point of view reacts, because that's what your customer will see, the perceived latency. So that's why you should have a proper CDN edge caching at the front. And then you can access one region, your compute, and your data layer. But we say that internet scale has to be global. Well, you can just deploy replicas in other regions, data replication on the database on the S3 side, or on the compute layer, it's more about deploying the same app into multiple regions if you use the proper infrastructure as code or deployment mechanism, API mechanism to deploy it seamlessly. So let's look at the details of this architecture. So the first one, as I mentioned, critical for internet application is to have a proper edge setup. So a few advice, best practices on this space, implement a web application firewall because you are public facing, so you have to protect from here. And leverage a CDN like CloudFront to cache data as closely as possible to your user. And also leverage the origins of CloudFront. Using behaviors, you can route your customer in different part of the application, serving the right tool for the right job. So if you have static assets, it's served by S3. If you have serverless compute, served by Lambda for short-term API calls, and you can also run your container application for low latency gap. And all of this is just routed by CloudFront. And lastly, something that is less known about is Lambda at the edge enables you to do more advanced routing, like bot mitigation, or you can have even one specific product page could be served by a completely different part of your architecture. Right, so talking about compute now. Well, we said internet scale, so you probably think, yes, I just need to auto-scale, and that's fine. Yes, you auto-scale using a metric, and that's the hardest part. So one big advice is think about not in terms of operations metrics, but more on customer business metric like queuing, order processed, numbers of connected users, latency perceived, and that's what the type of metric you should use for auto-scaling. Or you just be serverless, and in that case, you don't think about auto-scaling. Brilliant. But you still need to think about how you manage your concurrency on Lambdas, because you have some limitations on concurrency, and concurrency is not only requests per second, it's also a function of the duration of the Lambdas. So it's a numbers of how many functions run at the same time. So make sure you have the shortest Lambdas functions possible. And for this is the few advice is to be as synchronous as possible. And again, to go back to your customer as quickly as possible. So take the request, reply with an ID, and get your processing done at the back end with decoupling using something like SQS or step functions to have this proper management. Okay, but what about the data layer? So we talked about CDN, we talked about the compute, elastic scaling, deployed in multi-region, but the data layer is massive and very important. And our customers have been moving away from old guard database vendors to a different model, a model of the right tool for the right job. And this is a reference architecture. You will get all the slides afterwards, so I won't dive into all these details, but use this as a reference. But let's consider just a few examples. So if you have a order management, just use relational with strong consistency. Or if you want to scale very high, use a key value store backed by DynamoDB. And we have new use cases. So let's see how it looks from the AWS services perspective. For this, all these categories, and we really think that when you build a new application, you should use the right database for the right job and not have a large, very large database that have all the code and all the compute in it and all these different access patterns. We really think that when you design an application, you design it from the customer perspective and build from the access perspective and how you will access the data. So for example, that's why we built time streams, a time series data, very specific to time series. And we built QLDB, a quantum ledger database for cryptographic data, checked database, because our customer needed this. And all these databases can be worked together. And I will just take one example of one of our customers called Fender, which is the famous guitar builder, looked at ways of building a learning experience, building a learning app called Fender Play, fully on AWS. So they started to build this using the classic serverless stack with API gateway, Lambda functions, and DynamoDB, which was working very fine for the get me a new lesson, update a video, update a code, data, works very well. But then they thought about other use cases, like searching for a specific artist or specific type of lesson, and DynamoDB was not designed for this. You can't search in a fuzzy way in Dynamo. You just get data, put data, and it's very expensive in terms of time to search in a DynamoDB table. So that's why they introduced also in the mix Elasticsearch, which is another way of storing data and enable a fuzzy search or a more easy way to work. And it's very seamless between the two work together. So they reached like 40 invocations per second on the Lambda, terabytes in S3, and they're going global. It's a US company. It's around available everywhere. Just install the app and you can run it. So they designed it to be global by nature. S3 can be replicated to be close to your user. And Dynamo has this great feature called global tables, which is in a single click you can get a table in several regions. So with this, I wanted to give Phil the mic. Come on, thank you. On how they moved from MongoDB to RDS.
Okay.
Thank you.
Thanks. Okay, so my name's Philip, and I'm a software developer at The Guardian, currently working on the Guardian.com website, which hopefully some of you will have come across. But what I'm going to talk about today is products made by The Guardian's editorial tools team, which is the tool responsible for creating all the articles and live blogs that you see on the website. So the editorial tools at The Guardian is largely done in-house. So we have over 20 different microservices which handle everything from article creation, picture management, production following, all the way through to like really important things like crosswords. And we're almost entirely a AWS shop, mostly with a Scala backend, and then using a mix of React and Angular or whatever on the front end. The vast majority of our services are running straight on EC2 boxes with an increasing amount of Lambda as well. And from a database perspective, we're just using whatever tool for the job. So DynamoDB is the go-to for a lot of our smaller applications. We're using RDF, Elasticsearch for our picture system, which needs to handle searching over millions of photos and give pictures back to journalists as quickly as possible so they can report on it for live news. And we're using S3 as well for some use cases. So the tool I'm going to talk about today is it's called Composer, and it handles the publication of the 400 or so pieces of content that get published to the Guardian website each day. It's not a user-facing kind of application. So every time all the data from Composer gets sent off to a Guardian's content API via Kinesis, which actually handles the serving of the content for all our various applications. One of the kind of critical things with Composer is that we need 100% uptime, because if there's some kind of major news event, like a surprise election or some kind of natural disaster, we need to be able to send the alert out immediately. And I don't want to be the developer telling a journalist that the publication system's down in the middle of some kind of critical news event. It's also the source of truth for everything on The Guardian. So we've been publishing online for around 30 years now, and that's generated 2.5 million pieces of content, which is basically all we are, everything we've produced in that time. So it's very important we don't lose our data. And then because we store things like metadata, such as who was the last person to edit a particular article in Composer, security is very important, and so we have a hard requirement of encryption at rest for all data. But as I mentioned, it's not responsible for serving content. That's handled by a separate system. So this is the architecture we had before the migration to RDS. So it's a pretty standard setup. We've got an API there in the middle, communicating with a MongoDB database. And that MongoDB was just running on EC2 instances. It wasn't a managed setup. And then we've got two client applications, one serving the front end, which I showed the screenshot of, and then an integration system which ties up with all the Guardian's printing systems, crosswords, video, things like that. And then every time a change is made to a piece of content, we save it to the database, and we also post a message on a Kinesis stream to keep the Guardian's content API up to date. So why did we end up using MongoDB to start with? So this application was made about 6 years ago, and at the time we were coming off the back of the Guardian was using Oracle, and it was costing us a fortune, and we were basically looking for any kind of open source alternative. The motivation for going towards Mongo was that Composer started off its life as a live blog editor, but we didn't really know where it would be going next. And it ended up doing articles, galleries, etc. So having a document data store with a flexible schema was a great advantage. And we also didn't know how much we'd end up needing to scale this application. At the time, the Guardian was opening offices around the world, and we knew the CMS would need to scale as we hired more journalists. And to be honest, Mongo did the job for us. From a performance perspective, we didn't really have any issues. The trouble started coming as we started kind of managing it in the cloud. So about 3 years ago, the Guardian moved all its services from our basement in the office, which was vulnerable to lots of air conditioning outages, into Amazon. So we started running Mongo in the cloud together with management software provided by MongoDB. And probably the kind of biggest challenge we had with this was actually the difficulty of running Mongo. So the two longest outages we've had of the publication system at the Guardian have been as a result of issues with the Mongo data store. The first time was because we hadn't configured NTP properly, so that basically the time on our boxes got out of sync, and suddenly they couldn't authenticate with each other anymore. It's a very bad thing to happen. And in another case, the generation of a new index ended up causing some downtime of the database. So we're application developers. We wanted to be making tools for journalists, not spending our time doing DB admin. So we were really keen to move away from managing Mongo into some kind of managed solution. At the same time, the Guardian's not got pots of money, and Mongo was costing us a lot, both in infrastructure and in the support contract. So there was another motivation there to change our database system. So how do we end up picking RDS? So as I mentioned, we kind of had a preference for using something within Amazon Web Services because we were using it so heavily elsewhere. But we did consider other platforms as well. But at the time, none of them supported the hard requirement we had for encryption at rest. The obvious option then was kind of DynamoDB. We got a NoSQL document data store, and we want to replace it with DynamoDB, which at the time was Amazon's main document data store offering. But at the time, it only supported 5 indexes and didn't support encryption at rest. So for us, it wasn't an issue. Obviously, that's all since changed. Those features have been launched on DynamoDB. But we're using Postgres with success, fairly heavy in a lot of our other tools. We discovered that in recent versions of Postgres, there was support for JSON-B columns, which what we hoped meant that we could switch to RDS on Postgres without having to completely rewrite our schema into a kind of relational model and get away with a fairly kind of lazy migration by using the JSON-B columns for our content model. So that's what we did, and this is the schema we ended up with. So we've got 2 columns, an ID, and a massive content JSON-B blob, which is basically the same as what we had in Mongo. And the reason we get away with this is because about the vast majority of our queries are key value lookups. There's just a few cases where we need indexes on fields embedded within the document model. And we're running with this now live. We have been doing so for over a year, and we've got away with it. We haven't had any performance problems from this. But it wasn't straightforward. Some of the queries we were able to do in MongoDB were a bit of a pain to migrate once we were using JSON-B column for all of our data. So this is like my attempt at rewriting the add to set option, which we had available in Mongo. When I rewrote it into Postgres on this JSON-B column, it got a lot more complicated. So at the top there, you've got the kind of set content equals, and then doing the insert. So I should say that the add to set operation in Mongo allows you to add something to an array somewhere in your document model, and if it's already there, it won't add it. So in Postgres, it's a single line in Mongo. In Postgres, it looks more like this. So you have the command to actually add it somewhere within your document, and then the where statement to check that you haven't, that it's not already there. So it's not ideal, it's quite messy, it works. Another challenge was making sure that our indexes that were on that JSON-B column were being used and were performing well. So you can do indexes on JSON-B, but you have to make sure that any syntax you use to query the database is the same as the syntax used when you're creating your JSON-B index, which can catch people out because there's a lot of different ways of querying Postgres JSON-B columns as various different syntax. So how did we actually do this migration? So we found that the developers who, when we originally built this service, back when it was just a live blog editor just used for a few pieces of content, had been very bad and had put database code right down to the kind of controller level. So the idea of rewriting it and having the API talk to both Postgres and Mongo would have been possible, but it wasn't something we really fancied doing, having to untangle all that application code. So instead, we went for the option of setting up a proxy service, setting up a brand new API to talk with the Postgres database, and then a proxy service in the middle, which would forward all requests made to the legacy Mongo API to the new Postgres API. And the idea being with this that each time someone went to edit a piece of content or created a new piece of content, it would be kept up to date in both APIs whilst we were doing the migration. Obviously, some of our stuff is like 30 years old and probably won't be edited ever again. So to deal with that content, we just had a separate migration script which would fetch content from the Mongo data store and push it into Postgres with the proxy as a backup to kind of keep them up to date once they had been migrated. And then finally, to give us a bit of extra confidence that we'd actually done our jobs properly and that the new Guardian data store with all that valuable journalism in it was working, we used Gore, which is an open source tool to allow us to replay traffic from production into our test environment and check that we had the expected results. So this is our architecture for the migration. So we spun up a RDS data store and set up a separate API to communicate with it, and then had this proxy in the middle, which handled the forwarding of traffic. As well as that, what we did with the proxy was, as it made so it would receive a request, send it on to Mongo, get the response back, then forward it to Postgres, and then it would do a diff of the results that were returned. And any difference, it would send off to our ELK stack. So for those of you not familiar with it, ELK is basically based off the Elasticsearch database with a front end that makes it very easy to query your logging and create dashboards from it. So the hope was that by having this set up and the logging, as soon as that proxy stopped logging anything, we could be fairly confident that we'd done our jobs properly and that the new Postgres API was performing consistently with our old data store. So this is just a kind of example of some of the dashboards we were able to build with that ELK stack. We needed absolute confidence that all those kind of 2.5 million pieces of content had been properly migrated. So whilst our migration script was running back through from the historical data all the way through, it would post its results to ELK and give us an idea of how many pieces were there issues with, and gradually that number managed to get it down and down. The final kind of step before switching over to Postgres was to do a full migration of our production data store onto the test environment, and then use Gore Replay to capture like a sort of an hour's worth of traffic, and then replay it twice as fast on the test environment, so we could be sure that not only was the data correct, but also that the performance was sufficient for it. Because we really didn't know whether we were going to get away with this JSON-B setup, like how many problems that would cause once we had it at scale with hundreds of journalists editing at the same time. So once we had some confidence with this, we had the issue of actually changing over from Mongo to Postgres and treating that as the primary data store. And what made this kind of more difficult is that this picture looks really nice, but it's actually a lot more complicated than that. Because the Mongo API or the Composer API is not only responsible for communicating with the database, but also for sending message on Kinesis to ensure that our content API is up to date, as well as generating unique IDs and URLs for our articles. So we ended up with this concept of a primary and a secondary API, and we had to be absolutely sure that only one API was generating unique IDs at any one point. Otherwise we'd end up with kind of chaos. So we essentially had some application switches, which allowed us to switch off one application from talking to Postgres and change to the other. And then we set up routes in Route 53. So when it came to taking out that proxy and making the Postgres API the primary data store, we were able to just do that with a DNS change in Route 53 without having to make any deployments or changes to the application config. So it worked, we finished it, but it probably isn't the route I would take again if doing a similar migration. The main issue with this approach was that we had this proxy in the middle, which we'd expected to only be around for a few weeks, but was actually a critical piece of infrastructure on our publication flow. So suddenly, instead of just having the API and the client applications, we had this proxy and the Postgres API, and if the proxy went down, then so did the publication system. So it also, and in addition to that, it added an extra hop, which was not great for performance, especially because in some cases we were uploading audio files which had to pass through the proxy into both APIs. The other main issue with this approach, as I'm sure many of you will have come across, is as soon as you duplicate something, you duplicate the work required to do any kind of update. So if we added a new feature, like some kind of new, even if it was as simple as new image weighting, so suddenly you want half-width images on an article, you'd have to update the Mongo API and the Postgres API. And if you didn't do both, you'd end up with disparities, and we wouldn't be able to then safely migrate over. And then finally, as I've already mentioned, keeping track of which API was the kind of primary one that we trusted was a whole management task in itself. So yeah, probably the main thing, if I was doing this kind of migration again in this scenario, I probably would have started writing our Postgres application code within the same Mongo API, and then tried to, as much as possible, migrate one route at a time, rather than having this, what was ultimately a kind of big bang switchover, where Postgres API became the new source of truth. But kind of a good outcome was that we did get away with the JSON-B syntax. I'm still using it now. The only challenge is when you want to do some kind of query on an index field, and that's more or less prohibitive. So I don't know, recently I wanted to find a list of all the articles we had that had a tweet in them. And with our current setup in RDS, with just these two columns, it's not really viable without perhaps spinning up a snapshot into a really monster instance. It would just take too long, so that it's too painful to work with. But probably one of the best outcomes of this migration was that we're now on Postgres, and the kind of support online for any kind of Postgres query is incredible, because it's such a kind of established data store. You've got 10 years of posts on Stack Overflow. So when you've got junior developers joining, or almost anyone who doesn't have to touch the database very often, having to add a new functionality, it was really great for us having this kind of massive amounts of support online, even with using kind of legacy new features like JSON-B. The other big takeaway was that this is a really hot topic. We wrote a really long, detailed, quite dull article about why we switched from Mongo to Postgres, and it went crazy on Hacker News. So I think a lot of people interested in you know, what they should do with their Mongo databases or otherwise. Talk a bit about cost. So for us, this was a very important issue. Obviously, depending on your scale, these numbers won't be very interesting at all. But so when we were running Mongo, it was running on EC2 boxes because we needed high availability across 3 availability zones. We had 3 of them, and that was costing us $14,000. We then had some management software, which was shared between multiple Mongo clusters, but the kind of share of it that the Composer database paid was another $7,000 on top of that, just in infrastructure costs. And now with Postgres, we've got one R4 extra large box, which is still high availability, and we've made quite a big saving, so it's just $6,000 at the moment. That doesn't take into account support contracts and things, but from a purely infrastructure perspective, it's been like a good migration for us. So in terms of some things like that we're going to look at in the future with RDS, we've started using IAM authentication across other services. And then with GDPR coming up and the requirement to rotate your secrets regularly, this is like a lifesaver. It's a lot less scary than any other. In other cases, we're using lambdas to rotate our database secrets, but you're always worried that you'll get into a position where the application gets out of sync with this secret rotation service. So with IAM, it all becomes a lot easier. And we're quite pleased with how easy it was to just stick that into our application. We didn't have to change any of the database code. We're not currently using Aurora. That was initially because the size of the data store that we predicted was smaller than the kind of minimum Aurora database. We're now on an R4 extra large, and we will probably look to migrate to Aurora, partly for the performance increases, performance benefits, but also because of the stuff like IAMauth, which gets launched typically first on Aurora. So if you want it early, it's kind of an attraction for us. As I mentioned, this is like the Guardian's most important data store. So if the whole of Ireland goes down, which I don't think it ever has happened, but for us, that would be, we need total confidence that the backups of this data store are safe. So we've set up some lambdas to do cross-region replication of any snapshots taken by RDS. We ensure they're also copied to another region. And like from a DB admin perspective, whilst we were doing the migration, we were making all use of the kind of RDS logging and Postgres logs available. But now we're not really having to do anything. And I guess that's been the best outcome at all. I don't have to worry anymore that, that the database is going to go down, and I'm going to be having to rapidly re-remember how MongoDB works. So yeah, there's an elephant in the room, though, and it's not the Postgres logo. It's the fact that 8 months after we finished this migration, Amazon launched DocumentDB with Mongo support, which is a bit frustrating for us because we could have saved quite a lot of effort by just using a Mongo-compatible store in the cloud. I think ultimately we're in a better position now because I think for future features of the CMS, we're thinking about adding collaborative editing functionality in future. And we think that having a relational data store, which will eventually probably split out into more than just one column, will give us an advantage. But when we were planning this sort of many months of dev work to do the migration, there was no way we wouldn't have just gone to DocumentDB if that had been an option. Yeah, that's everything. So yeah, I'll stick around afterwards if anyone's got any questions. But I'm now going to pass back to Bastien to talk about a more real-time application use case.
Thank you. Thank you, Phil. It was very interesting and on the point of which database to use and how our customers really leverage this to get to the next level of architecture. So, thank you. Before wrapping up, I wanted to talk briefly about real-time applications. And so before explaining why it's important and what is Elasticache, especially, let's take a step back and talk about why it's important. It's if we go back to our users that are global, that now include data that needs to be more real-time, like when you deploy an online game, when you are doing high-frequency B2B exchange like financials or others, everything needs to be with the lower latency that we used to have. And that's something that you can't really achieve. Even with the more advanced database, you always have to have something in between as a caching mechanism. And that's something that can do Elasticache to have your data closer to your user. That's only one part of the story on caching and low latency. We talked about CDN, we talked about Lambda at the edge, everything that can be closer to your customer, closer to your user. Or when you think about IoT, it can be also closer with something like green grass. But here I wanted just to focus on this, focus on Elasticache, which is one of the best use cases for Elasticache is running internet applications because it's extreme performance with sub-milliseconds response time, so very good for online interaction. And even your classical messaging app expect a very low latency interaction. It's fully managed. We heard from Phil, it's great to have a managed database because that's not a heavy lifting you want to take over. And running a Redis or Memcached, which is actually what is running Elasticache, It's not an easy task. It's quite hard to get a proper cluster. It's a bit like the MongoDB running at scale, running a cluster at scale can be challenging, and this is a heavy lifting. And this is what we learned from all the customers that we bring back to you. And easily scalable, it's very easy to scale using read replicas and also write using sharding across multiple availability zones. And that's really integrated into Elasticache. So that's a reference architecture on how you can cache your data that are either stored on Dynamo or on RDS. So you have here 3 choices of when your application, whatever it is, can write to RDS or to Dynamo. It can also write through Elasticache, and all the other components can be updated. So when you write, for example, to RDS, you can have a Lambda function that is at the back of it and running asynchronously, writing through back to the caching layer. And the same for DynamoDB. When you write a new item or update a new item, you can have what we call DynamoDB streams that can stream all the changes, and all the changes can be then written back to, for example, in this case, Elasticache. So to wrap up this talk about internet scale application, you have this reference slides. Again, it's quite heavy read, but that's something you can take away. But that's really what we wanted to give you today, is how to choose which service in which situation. And you are not now tied to one vendor. You can just, based on what you want to achieve, that's probably a good solution on AWS. If you want to just lift and shift an existing application, it's probably going to be an existing relational engine like MySQL, or the commercial engine SQL and Oracle are totally running on on RDS, and you run DMS to migrate data. And if you look at more new application that you build from the scratch, probably you should look at something like DynamoDB and look at the new options like time streams data, blockchain are a new trend, but also because our customers are actually looking for a more structured data around blockchain. So that's why we launched QLDB. And on the bottom of the table, you have all these analytics offering coming from a S3 data lake or any data lake. You can run analytics using Redshift or using all other tools like EMR and QuickSight to display. Okay, so to wrap up, if you had like 4 points to take away from this talk, that would be, first one would be caching at the edge with the CDN, locally behind your compute, as much as possible and as closely as possible to your customers, and now it's easier to be done using the technology. Scaling is possible using AWS. Think about business metric and leverage the serverless and containers offering, which have scale integrated into it. Use the right tool for the right job. That's especially important for database. Using purpose-built database, you get the right performance and the right usage for your access pattern. And don't be afraid to use multiple databases in your same app. That's absolutely fine. And go global, leverage the AWS regions and the replications mechanism built in our services to easily go global and deploy your application. Thank you. These are our contacts, me and Phil. Please feel free to reach out on Twitter, email, and we'll be around for any Q&A if you have in the corridors at the back. And please complete the session survey. We really value your feedback on our work, on our sessions, and leave the headphones for the next sessions. Thank you.